Welcome to the part 3 of this 4-part series on intervals of kinematic equations. The third type is reaction time. And it turns out the average reaction time for a human is 0.25 seconds for something they see. When it comes to a sound, the visual stimuli is 0.17 seconds for us to react. And then touch is even faster at 0.15 seconds. When driving, we often come across this situation where the light changes on us and we have to react to that. And this stimulus is a visual, audio, or touch. Well, it's something we see. So it's 0.25 seconds if the person sees that and then reacts to stop. Now, in reality, do people always stop at yellow lights? There's a little more decision making there, so maybe it takes a little more time to decide to press the brake. But if you have that immediate reaction, that's kind of the delay for you to actually start decelerating to a stop. So this is actually an interval problem, right? It's not as simply as like you immediately start slowing down, right? There's going to be a time period. You're going to continue to move. You're going to move from a point A to point B, and that's just you just continuing at doing whatever you're doing. You're moving at constant velocity, and then once you processed what's happening and then started to you've hit the brake. Now you're going to now do the deceleration. You're going to be slowing down to a stop. So this is often this total displacement here from DAC. This is often referred to as the total stopping distance. This is the total stopping distance. And you may notice that some lights are yellow for longer than others. It depends on the speed limit for that road because we need to allow for a little more caution when moving at faster speeds. So in this first interval, we're just moving at our constant velocity in this problem, right? This is our first acceleration. It's just 0, right? This question says we are starting at a constant velocity of 25 meters per second east. So let's write that in. And clearly I've said that east is to my left, to my right. And I'm saying those are going to be my positive values and west is going to be my negative direction. All right, so I'm starting with this initial velocity of 25 meters per second. That's my VA. I'm actually going to be moving at constant velocity, so my velocity at VB this time it's going to still be the same. It's still going to be 25 meters per second. So VA is going to equal my VB. So actually, what I'm going to do, I'm just going to change this little subscript. My VA and VB are actually equal to each other, and they're equal to 25 meters per second east. And the light suddenly turns amber. Yep, so we had to react. So there's this is our reaction time. My time from A to B is, if the person just immediately reacts, is going to be 0.25 seconds. And then the person reacts and then slows down to rest. So my final velocity, like at rest, my VC, I'm going to be completely at rest at that point. And then my acceleration during this interval is going to be 3 meters per second squared west. And the first thing we should do is make sure all of our variables are going in the same direction. So I'm actually going to express this is my acceleration 2. Because it's going in the west direction, I need to express it as negative 3 meters per second squared east. So when I put these values into my formula, everything is related to east. And then so my positive values are going to be east and my negative values are going to be west. Okay, so we have to go through this process. Our end game is to figure out what the displacement is from A to C. So we need to figure out what the displacement is from A to B and then from B to C and put that all together. So given what we know, in this first interval, it's actually a constant velocity, right? So I can actually use, I'm just going to do this for VA, but the displacement is going to be from A to B, and my time, which we know by looking at the average reaction time, is 0.25 seconds. So we know our velocity and our time, we can just solve for our displacement. So we got VA, our time, and we've got 25 meters per second and time of 0.25. All right, so like how much do we actually travel? Well, that's about a quarter of 25. So we actually travel 6.25 meters. So while we're just immediately reacting, we've traveled that far. And then let's figure out how far we move while we're slowing down. So in this case, we have to use our kinematic equations. Let's think about what we know. We actually know our final velocity, we know our initial velocity, and we know our acceleration. And what we're trying to get here is displacement from B to C right now. So this is what we're trying to get. So choose from your list of kinematic equations to figure out which one involves those four variables. And the one that you'll need to use is this one, VB squared. This is actually going to be VC, so it's V final squared equals your initial velocity squared plus 2 times your acceleration, this is acceleration 2, times your displacement. So we're going to need to rearrange this. You can substitute your values in or rearrange it with variables. I'm going to do it with variables, so I'm going to end up bringing this over, and then I'm going to, by subtracting both sides, and then I'm going to be bringing this over by dividing both sides by 2a. So the way it'll look in the end is we'll have VC squared minus VB squared, and then that will all be over my 2a2. All right, let's put in our values. We've got our final velocities is 0. That's just 0 squared minus my velocity, which is given in the question, my velocity at B, right? We were at constant velocity, so it'll still be at 25 meters per second. And then I'm going to put in my acceleration, which is negative, right? It's because it's west, it's going to be -3 meters per second squared. So be careful of that. And we're going to now do 25 divided by 2, divided by 3. So it's actually 25 squared, be careful. That would have not been good. So we got 25 times 25, and then 2 times 3 is 6. So we're going to 625 divided by 6 is 104.17 meters. Now, that's a pretty gentle acceleration, right? That's pretty far to travel. Typically, we don't travel quite that far, but it's not actually unreasonable to travel that far when slowing down from that kind of velocity. So here it is. Here is our displacement from B to C. So if we're looking at the total stopping distance, that process of stopping, so it's sometimes called total braking distance. But anyways, so we're looking at that is going to be our first variable, first interval's displacement, where we're just kind of reacting. We're kind of just processing it. And then here is our actual deceleration. This is how far we traveled there. So we just add those together and we get 6.25 meters plus 104.17 meters. And that gives us a result of 104.17. We get a final result of 110.42 meters, and this is to the east. Let's box that final answer and write our conclusion. Therefore, the total stopping distance is 110.42 meters. There you go. The final type we'll look at is these meet and chase problems, where you actually have two different objects doing two different things, or we have one with maybe two runners moving at their corresponding constant velocities, but one has a head start, and we're going to see how far down the road it takes to catch up and surpass that other person, answer questions related to that. All right, I hope this helped, and see you in the next one.